Okay. Can you tell us a little bit more about that?
Sure. You may wonder why I didn't do a PhD in SETI. Okay,
Right.
but that's sort of got chances of success are fairly small. But it'd be an awesome thesis if
you
you
found
found something. Yeah.
Right.
So, but anyway, an interest I always had was in the life cycle of stars, and particularly at the end of the life cycle. And supernova remnant is what's left over after a star has exploded in a supernova, and the remnant is what enriches the space, and basically what we're made of from Stardust. Yeah.
So can you just give us an idea of what the life cycle of a star is?
Sure. So a typical star, like our sun, is probably a second or third generation star. So the very first stars would have been probably just pure hydrogen. That was the first element in the universe, and it's just a collapsed cloud of gas that has become so dense that in the center the forces of gravity pushing all of the molecules together eventually gets hot enough to start nuclear fusion. So the elements will fuse into helium, and then the helium into the heavier elements, and so on, and that starts, if you have enough gas, becomes a star.
Right. And why does it collapse?
Gravity.
Okay.
Like everything, gravity. It pulls everything together.
So as the hydrogen or these gas clouds, as they slowly come closer and closer, the gravity builds up and the heat builds up, and that provides enough energy for the hydrogen atoms to
fuse together. You have to have enough gas because you need sufficient gravity to produce those high temperatures to get nuclear fusion to start, and you need a whole bunch of balances, because if the cloud is too hot, then the molecules are going to be moving around too much. It's not going to collapse in on itself easily. It's got to be cool enough to collapse, and once they do collapse, you've got to have enough of it to spark off fusion. You've got to have enough gas there, so excuse me, so that when it collapses in, the forces pushing out, there's enough holding it then. So a star is effectively in a balance of forces pushing out and the gravity pulling in. So
the forces pushing out comes from the
from the
fusion.
Radiation and the fusion. That's the radiation pressure that's pushing out, and the gravitational forces pulling everything in. And you've got to have that right balance, and if you get it right, then you'll get a star.
And so as a star ages, does that balance start to change?
Yes. So depending on the size of the star, if it's a large star, a lot of mass, then you're going to burn hotter. And when I say burn, I'm not talking about chemical burning. I'm talking about nuclear reaction fusion. It's going to burn quicker and die younger. So it quickly goes through its life cycle. A star like ours is not that massive, so it sort of burns slowly, has a longer life cycle. But the life cycle means that as the fusion takes place in the center, you're fusing and becoming heavier elements. So it's a bit like an onion. So you get concentric zones where you've fused, the elements have fused, the hydrogens become the helium fuses, and so on. You get all of the heavier elements until a point where you get up to iron at the core, and you can't fuse the iron because you need more energy in to fuse it than you'll have got. So at that point, you stop the fusion process, effectively stops. You've still probably got fusion going on in the outer shells, but it starts to cool down. And depending on the size of the star, if it's a star that's about 3 times the mass of our sun, then you will go off in a supernova when you've run out of fuel, because it basically crushes down on itself so quickly, it gets to a point where it can no longer get any more compact, basically, so and you get a shock wave, and that's when you get the supernova explosion.
So because that energy isn't there to keep it from collapsing, it collapses.
Yeah.
And
it bounces back, as it were, and that
bounces
sets
back.
up a shockwave, and that's starts the supernova explosion.
Okay.
That's if you're 3 times the size of our sun. If you're about the size of our sun, what happens is you just get bigger and bigger, because now the gravity can't hold it together, as it were, and there's no extra fusion going on, and you'll get one of these beautiful things that we call a planetary nebula.
Right.
So basically, it just slowly cools and disperses out. So it doesn't go off with a big bang. It
it just slowly
dissipates.
Just a question. So you said, so shouldn't our sun also collapse, considering that it doesn't have that energy to keep it from collapsing? Why does it get bigger?
No, it will collapse, but the outer shells, there's nothing to hold that. So the outer shells effectively just will come off and be pushed away from the radiation that's on the inside.
I see. So the inside collapses.
Yes. But it won't collapse to the point where it'll cause a supernova explosion. Yeah.
Okay. And so are there stars that are smaller than our sun?
Yes. Yeah, brown dwarfs and things like that. So they're smaller, colder. I guess Jupiter is probably a star that never was, because it just didn't have enough gas to get fusion going. But Jupiter is, one of the gas giants in our solar system. Just not quite enough gas to actually get fusion going in the center.
Okay, this is a dumb question, but what if you send like a nuclear bomb to Jupiter? Could you start off the process?
You possibly could, but I don't know that it'd self-sustain, and you'd have to get it right in the right place. That bomb right in the right place to kick it off.
Right. Okay. So you're looking at the remnants of supernovas. So you're looking at the stardust, essentially.
Yeah, you're looking at what's left over. So it's the material that's been ejected from the supernova explosion. So that material goes into the interstellar medium, and it pushes out with that matter, and it sets up that shockwave that makes that shell expand, and that is what's enriching the interstellar medium with the heavier metals and the materials, effectively the stuff that allows us to be made. I mean, we know that the sun must be a second or third generation star, because we're here. The Earth is here. The core of the Earth is iron. So there must have been a star at some point that exploded and created those metals and materials that we are effectively made from, the carbon and so on.
Yeah, and that wouldn't have been possible as a first generation star, because
all that would have been around was hydrogen basically. Yeah.
Huh. So what questions were you trying to answer in your PhD?
Well, just looking at the mechanisms of the enrichment, and looking at how we could try and tell what type of explosion created that particular remnant, because there are different types of supernova, all depending on the energy and sizes of the initial explosion. So a remnant could be thousands of years old. So the original supernova explosion, nobody has actually seen that. So trying to work backwards, it's like trying to get our models more accurate, so that we can then simulate working backwards, try to figure out what was the proto-star, the star that actually created that remnant.
So you're like a crime scene investigator. You're looking at what's left behind by the criminal, and then trying to figure out what happened.
Exactly, yeah.
That's interesting. So each type of supernova would exhibit a different residue or stardust.
Yes, yeah, and it all... many variables there. I mean, like the environment it's exploding into will produce something different. You could have two stars exactly the same size and so on, and they'll go supernova, but the environment they're in, it could be different, and so you'll get a different remnant at the end of that. So, that's another variable there. So it's not like you can just say, oh well, that particular thing's got this shape, so it must have been this sort of star.
Right.
Well, it depends the environment it's in as well.
Right. That's interesting. So there's a lot of variables there.
There is a hell of a lot of variables, and it's not like most science. Astronomy and astrophysics is not like most sciences where you go in the lab and can test that, because we don't have another universe to play with and vary the variables. Though that's why we use computers a lot. We build universes in computer simulations and test those and see how our models hold up, whether we can produce something that resembles what we have in nature. What we see in nature.
Thanks for listening to Blab Codes. Rate and review our podcast on iTunes or wherever you get your podcasts, because it does help us spread the word. And if you like what we're doing here, then help us grow it by sharing this with a friend of a friend, or your mailman, even your mailman's mailman. We also want to hear from you, so send us questions or comments to blabcodes@gmail.com. And if you have any interesting questions or comments, then we'll talk about it on air.